Okay, so today, before we actually get into group actions, let's go over some properties of normal subgroups. Not really properties, let's go over some topic that is related to homomorphisms and isomorphisms, the inner automorphisms, right? So let me write normal subgroups and inner automorphisms. Okay, now as a quick reminder, for a given group G, we say that N is a normal subgroup of G if and only if, this is by definition, if and only if, for all G in G, for all elements that we take from the group, for all elements that we take from this N, we have the element G inverse NG to be in N, right? Now, observe that this actually works for any G and any N that you take from this normal subgroup. So instead of saying G inverse NG is an element in N, we can somewhat modify this and write G and G inverse belongs in N. That would once again be the same thing, right? What do we do in this case? If I take this to be 1, how do we show that? If I take this to be 1, in the definition, what we are going to do is replace this G by G inverse. We can do it. Why? This element must belong in N for every G, for every element that you pick from the group G, right? If G is an element in G, because it's a group, its inverse is also in there. So what we're going to do is, in 1, let's replace G by its inverse so that we can see this G will be replaced by G inverse. So the inverse of the inverse times N times G inverse, which is simply the inverse of the inverse is this element itself, NG inverse, belongs in N, right? It belongs in N. Right. Now, keeping this in mind, let's move on to our first definition. What we're going to do is we are going to define an automorphism of a given group G. An isomorphism phi from G to itself. Now this given isomorphism phi is from G to itself. This sort of isomorphism is what we call an automorphism, right? So it's a bijective homomorphism from G to itself. An isomorphism phi from G to G of a group G with itself is an automorphism. Automorphism of G. Right. Now, with this, we define the inner automorphism. The specific automorphism we are about to define, the automorphism, which will be denoted by I sub G. from the group G to itself defined by I sub G of X is equal to G X G inverse, right? The same sort of type of element that you can see over here. For all X in G is the inner automorphism of G by this element simple G, which is also taken from the group G. So how do we define this inner automorphism? First, we fix an element simple G in the group. Then we define this function with respect to that. This is why we call this function inner automorphism of G by the element simple G. Right? Okay. So when you perform this automorphism on any element X, we call this conjugation of X by G. So let me write it. Performing Ig on X is called conjugation of X by G. Right? Now, even though I gave it as a definition, let's prove that this is in fact an automorphism. Okay? So let me write. For a group G, Ig by definition is given by Ig of X is equal to G X G inverse. This is for every X in G where we have a fixed G. Let me put it this way. We first of all fix the element, then we define this mapping from G to G, right? So let's prove this. Ig is an automorphism. It's an automorphism. Okay. So what is an automorphism once again by definition? It's an isomorphism from G to itself. So what exactly it we can see that the function is defined from G to itself. You take any element in G, what you get at the end, for any element that you take X from G, it will be mapped to the element Gx G inverse. G is an element in the group, X is an element in the group because it's closed under the binary operation. This element that you see on your right is an element in G. So we can easily see the mapping is actually from G to itself, right? It's a well-defined mapping. Now, all we've got to show is that this I sub G is an isomorphism. So, we have to show that it's a bijective homomorphism. What do we mean by a bijective homomorphism? A one-to-one and onto homomorphism, right? So, first let's show that this is a homomorphism. Let me write, first of all, we need to show that is a bijective. One-to-one and non-to homomorphism. Right. So to prove that this is a homomorphism, let's take two elements x and y from G. We have to show that I sub G of x times y is equal to Ig of x times Ig of y, right? So the first step would be to pick two elements x and y. For x and y, two elements in G, we have IgXY. By definition, this is equal to G times XY, G inverse. How can we move forward from here? We have to show that, we actually have to show that IgXY is equal to IgX times IgY. This is what we have to show. How do we move forward from this step? Any ideas? We can actually write now. What should we get as I sub G of X? This element is simply Gx G inverse. And this element would simply be Gy G inverse. So if in this product we have Gx G inverse times Gy G inverse, then we are done. So between x and y, we must have G and its inverse, right? And we know that it's easy to incorporate that product because x times y, I can write as x times E, where E is the identity, y, G inverse, right? By definition of the identity, we know that identity times any element that you take from the group will give you that element. Right now, this identity I will replace by G inverse G because with X we want on its right to have G inverse. When it comes to Y, we want G to be on its left, right? So instead of writing G inverse, I will replace E by G inverse G, which we can do. All this is coming from the definition of an inverse. Y G inverse. Now we simply apply associative property and simply consider this product separately times Gy G inverse. Now by definition of the function I sub G, we see that this is Ig of X times Ig of Y. And therefore by definition of a homomorphism, we see that Ig is a homomorphism. We say that this is a homomorphism. Now we have to show that this function is one-to-one as well as onto. Right. So to show that this is one-to-one, let's take Ig of X to equal I sub G of Y. Then by definition of this function, we replace this I sub G of X by G X G inverse. This is equal to, we replace it using the definition of the function, G by G inverse. Now what do? We take, now what do we have to show at the end? We have to show that X is equal to Y. So how do we go about proving that?
Multiply both sides by G inverse and then G.
Yes, very good. So we multiply both sides on the left by G inverse and on the right by G, which we can do at the same time, right? So on the left, we put G inverse. We have Gx, G inverse. And then on the right, by G. Once again, using the associative property, we see that this is G inverse G times X, G inverse G. Same on this side, G inverse G times Y, G inverse G. What we have? By definition of the inverse, G inverse G is simply the identity. And over here also we have the identity. So we have identity times X times the identity. So the definition of the identity gives you all this simply to be reduced to X. Over here also the same, reduced to Y. Right? Therefore, by definition of a one-to-one function, I sub g, the function, is 1 to 1. Is 1 to 1. Now we have to show that this function is onto. Now we have to show that this function is onto. So what do? We take, now Ig is actually from G to G, right? So we take any element in G. Any element in G, we want to see that there is another element in G which will be mapped to this particular element through the mapping I sub G. So let's take y from G. Now observe that when you take I sub G some element, that must equal y, right? That must equal y. So you're taking y from G. Simple G is already a fixed element that is in the group, right? So we must have G inverse yg also to be an element in G, because G inverse y, they are all elements in G, right? So their product, this is closed and its binary operation, so this element is in G. Now see what happens when I map this element through this function ig. G inverse yg is equal to, by definition of the function, G times the element times G inverse. Now we use the associative property to get this. This is equal to what? Y. So for any element y that you take from G, G inverse yg will be mapped to it through the mapping G. Therefore, this is an onto function, by definition of an onto function. So now we have shown that it's a bijective homomorphism and it's from G to itself. Therefore, this is an automorphism, by definition of an automorphism. Therefore, IG is an automorphism. It's an automorphism. Right. Now observe, let's take any normal subgroup of the group G. Now this is not a part of the proof, end of the proof, right? Let H be a normal subgroup in G. Let H be a normal subgroup in G, right? Then we know for any H element that you take from this normal subgroup, we have I sub G of H. By definition of the map, this to be G, H, G inverse. Now what you get as this element, what you get, the function value, is actually inside H, This is because H is normal in G, and we have seen that in that case, this will also be an element in the normal subgroup, right? That's the first thing that we actually showed today. Right, so you take any element from the normal subgroup through the mapping. The function value of that element will also belong in H because H is normal in G, right? Because H is normal in G. Now, see if we calculate the image of H under this function, if I write Ig of H, this is equal to what? By definition, all function values where simple h comes from this normal subgroup, right? This is equal to G inverse where all this h comes from h, right? So G is fixed over here, G inverse is fixed. All these values that are here in the middle, they come from the group H. This is equal to what? G, H, capital H, G inverse, this set. Okay, now this I will simply say is equal to H. Why is that? Why do we have this set to equal H? Because H is a normal subgroup in G. When H is a normal subgroup in G, we know that GHG inverse or even G inverse HG is equal to H. We have proved this theorem also in a previous lesson. Right? I will simply put it over here. H normal in G implies, if and only if really, GHG inverse equals H for G in G. Right? So we see that normal subgroups of any given group G are really not changing under any of the inner automorphisms. Now, I sub G is any inner automorphism because this simple G is chosen arbitrarily, right? So no matter which element that you take from the group, through this inner automorphism, the image of H will simply be itself, right? In other words, for every inner automorphism, the image of H through Ig will simply be H. In other words, it will be invariant, any normal, and H is any normal subgroup of G. So we can conclude that any normal subgroup will always be invariant under any of the inner automorphisms, right? Okay, so let me write it here. Normal subgroups of a group G are invariant under all inner automorphisms. All inner automorphisms, right? Okay. And then we have one last definition before we actually move on to group action. A subgroup K of G is a conjugate subgroup of H If K is equal to the image of H under this inner automorphism for some element in G. For some element in G. Right? Now, coming back over to this case, when H is normal in G, we can see that through any inner automorphism, H will be mapped to itself, right? So I sub G of H is equal to H. This does not mean that you take any element from H, it will be mapped to itself. This simply means all of H will be mapped to all of H. H will simply be mapped to H. So through this inner automorphism, if this is the identity, which could be, right, then every element in H will be mapped to itself. In any other case, we are simply looking at some permutation of H. We could have H1 to be mapped to H2, H3 to be mapped to some other element somehow, because it's a one-to-one and onto function. After you map every element of H, all the function values will give you H back. That's it. Okay? Right. Do you all have any questions?
No, madam.
Right. Now we are going to start group action. Group action on a set. Right. So before we actually define the group action, if we recall how we defined a binary operation, right? How did we define the binary operation? It's a function. I will not write all, but as to see the resemblance, okay? Usually denoted by star is a function from G cross G to itself, right? What do? We take some element from this product G cross G. So let's take G1, G2. It's a binary operation because we are taking two elements. Once you apply the rule that is given by star, what you should get is an element in G, right? Element in G. So now, keeping this in mind, let's go to the definition of a group action. Let X be a set and G be a group. Now, an action of G on X. What does this definition actually gives you? It gives you the way G acts on some set X, some other set X, right? So X need not be a group. It's some set. An action of G on X is a map. Let's call this map phi from G cross X to X such that or satisfying the following two conditions. First thing is phi of the identity and X. When you take this pair, now observe the first element, these are ordered pairs, right? And this resembles an element in G cross X. So the first element in this ordered pair is an element in G. Second element comes from X. And the identity is an element in G. So when you take the identity and X, this pair, this element from this given set, this should equal X for all X in X. This is the first condition. The second one is phi of, let's take for any two elements G1, G2 in G, G1 times G2 is also an element in G. So let's take the pair. Let's take the element from G cross X to be G1, G2, X. This should equal phi of G1, phi of G2, X. This is for all G1, G2 in G and for all X in X. For all X in X. This is what we call an action of G on a set X. Now, if you compare these two, the binary operation is also, because as you can see, these conditions are satisfied even in a binary operation. You can think of it as, you can not think of it as, sorry, you can see the similarity over here, right? In this case, if you look at the binary operation, X is G itself, right? X is simply G because a group is a set together with a binary operation and satisfying certain conditions, right? So now in this case, once you apply this function to any pair that you take from here, what you get is an element in X. What you get is an element in the set X, right? Now, to somewhat simplify this notation, let's write G dot X in place of phi of G comma X. Now observe this dot does not in any way resemble the binary operation over G. This is simply written in place of phi of Gx, right? Phi of Gx. So with this notation, the above two conditions can be written as first one, phi of Ex, this simply will be E dot X. This is equal to X for all X in X. Second one, this will simply be G1, G2 dot X. This should equal G1 dot G2 dot X for all G1, G2 in G and for all X that you take from the set. Okay, now under all these conditions, if all these conditions are met, then we say that this X is a G set, or we say that G is a group acting on a set X. So let me write this also. Under X is a G set and we say that G is a group acting on a set X. G is a group acting on a set X. Right, let's take a look at one example. Do you all have any questions from this? Let's do one example, then you will understand. And after that, you can ask any question you have. Let's take X to be 1, 2, 3, right? And let's consider the group S3 with the permutation group of permutations of these three elements, really. One, then we have 1, 2, 1, 3, 2, 3, 1, 2, 3, and 1, 3, 2. All given in their cycle decompositions. This is the group of permutations of X. Right. Now let's define P from S3 cross X to X. By phi of any permutation, let's denote it by sigma, an element in S3, X to equal sigma of X. What do I mean by this? Now remember, sigma is a permutation. In other words, it's a function, a bijective function from X to itself, right? If you recall, if I take sigma to be this cycle, 1, 3, right, containing these elements 1, 3, what does it mean? Sigma is a function from X to X, which maps 1 to 3, 3 to 1, 2 to itself. So it's a function, right? And this simple, now let me write, sigma is in S3, X is some element 1, 2, or 3, right? Okay, so what do we mean by sigma of X? Now we understand sigma is a permutation. In other words, it's a function. So what we have over here is simply the function value at X. So the function value at X. Now to see that, so let's write, in other words, let's go to our usual notation. Instead of phi of sigma comma X, let's write sigma dot X equals sigma of X, right? Sigma of X, right? Just to calculate maybe a few and see what it actually gives you. Let's take sigma to be 1, 2, the permutation. So if I write it separately, this is the function sending 1 to 2, 2 back to 1, 3 is fixed because you can't see it over here, right? Now let's calculate sigma dot, let's take 1. Let's take 1. So we have 1, 2 dot 1. By definition, this is 1, 2 of 1. We want to see where 1 is sent to through the map sigma. And we know that 1 is mapped to 2, right? Or you can simply go to this cycle. You can see that 1 is mapped to 2. This is equal to 2. An element in X. Let's calculate 1, 2 dot 2. Another element in X. 1, 2 of 2, or the function value at 2, sigma of 2. 2 is sent to 1. This is equal to 1. And the last X value, which is 3, what does this equal? What does this equal?
3.
It's equal to 3 because through sigma, 3 is fixed. In other words, 3 is sent to itself, right? So we got all values that are in X. Okay. Now to see that this is indeed a group action, we had to show that the first condition is satisfied. We have to show that the first condition is satisfied. The function is well defined. We are simply getting the function values of all these permutations, right? Now, to see that this is indeed a group action, we have to show that E dot X is equal to X for all X in X, right? Now, to prove this, first, we have to know what the identity is. Identity is simply shown over here, the identity permutation. The identity permutation, right? So, identity permutation dot X, by definition of the group action is given by identity function of x. What does this equal? For any x, now this 1 resembles, once again for your convenience, I'll put it over here. The identity mapping simply maps 1 to 1, 2 to 2, 3 to 3. So no matter which element that you pick, it will be mapped to itself. So the function value of this is simply x. For any x that you take from the given set. Therefore, the first condition is satisfied. Now we have to look at the second condition, which is this: g1 g2 dot x must equal g1 dot g2 x. Let me write g1 g2 dot x g1 dot g2 x. Okay, this is what we have to show for any g1 g2 that we take from the group, and any element x that you take from the set. Okay, so now let's take any two permutations from S3. So these permutations once again are bijective functions from x to x. We are simply permuting elements of x. Sigma 1, sigma 2, let's take from S3. And let's take any element x from the given set. We have phi of g1, sorry, not g1, g2. Phi of sigma 1, sigma 2, x is equal to, by definition of the group action we have defined over here, what you see over here as a multiplication, we have sigma 1, sigma 2 of x. What do we mean by multiplication over here? So it's given as a product. What does it mean when you see the product of two permutations? This is simply function composition, right? Function composition, composition of these two permutations. Even though we are using the word permutations, we know to be functions, right? So in S3, the binary operation is function composition. So what you see over here is simply sigma 1 composite sigma 2 of x. Function, from the definition of function composition, we can write it as sigma 1 of sigma 2 of x. This is sigma 1 of sigma 2 of x is simply sigma 2 dot x, or in other words, phi of sigma 2 comma x, right? Now this, on the other hand, is simply sigma 1 dot sigma 2 dot x. Exactly what we wanted to show. So the second condition is also satisfied, right? What you see over here is what? Phi of sigma 2 comma x. So this is simply phi of sigma 1 comma phi of sigma 2 comma x. We will simply stick to this notation, okay? Unless we have to go with this one. Right. Do you have any questions?
No, madam.
Right. Then we will do more examples. Before that, let's get to a theorem. Okay, let X be a G set. What does it mean? That means G is acting on X. There is a group action so that G acts on X. Okay, by definition. For each element G that you take from the group, the function sigma g from x to x defined by sigma g of x is equal to gx, right? For x in x is a permutation of x. Also, the map P from G to Sx. This is the group of permutations of x defined by G. Phi of G by phi of G equals sigma G is a homomorphism with the property that P of G of x is equal to Gx. Right? Okay. Right. So there's a lot of details in this one. First is X be a G set. That means there is a group action. So before we even begin in the proof, let's start by identifying what this group action is. Let's define this group action by phi prime because we already have this function phi over here. So it is from G cross X, from G cross X to X, Y, X is a G set. So the group that has to be here is simply G. And let's write phi prime of G comma X will simply be Gx. Simply be Gx. This is what you see over here. This is what you see over here, right? Now we are going to simply denote this by Gx. So we understand this Gx is actually an element in X. Because you take any pair of elements from here, through the group action, you get another element in X. So this Gx is an element in X. This function is all well defined. So X be a G set. For each G, we take an element from G. For every element that you pick like that, you can define a function sigma of G from X to X. How do we define this function? Take any element from X and map it to Gx, which is the element that you get through this group action. Right? Now we say that this is a permutation of X. This map that you see over here is a permutation of X. Right? So what does it mean? You have all these elements in X. You take each element one by one, map it to either the same element or some other element in X. Once you consider all function values, you should get all the values of X. Those should be permuted here and there. Those should be permuted. And then so that this is a permutation. So how do we prove that this given function is a permutation? To prove that it's a permutation of X, we only need to show that it's a one-to-one and onto mapping. It has to be onto and one-to-one to see a permutation. Right? For example, in the previous case, you have this sigma to be a permutation of X. X has elements 1, 2, 3. So this is a permutation of X. 1, 2, 3 is permuted to 2, 1, 3. Right? 1 is sent to 2, 2 is sent to 1, 3 fixed. So in order to show that a given function is a permutation, all we have to do is show that it's one-to-one and must be onto. Right? So that is the first thing. We had to show that this sigma is a bijection. In that case, we simply deduce it's a permutation. Then we have to show that this map phi from G to Sx, this is the group of permutations of X, right? So it's a group of permutations of X. Once we prove that this sigma G is a permutation of X, this element belongs in Sx. So this is also well defined. It's a homomorphism. We had shown that this is a homomorphism with this given property. Right. So first thing is we had to show that we had to show that sigma G is a permutation. So in order to show that is a permutation, we need to show that sigma G is 1-to-1 and on-to 1-to-1 and non-to. Okay. So to prove that it's 1-to-1, let's take x1. Now this is from x to x. So let's take x1, x2, two elements from the set x. Then sigma g of x1 equals sigma g of x2. Sorry, x2 implies that by definition of sigma g, we have it to be gx1 equals gx2. Instead of writing g dot x1, I will simply write gx1, right? gx2, right? Now, this simple g is taken from g. So its inverse, g is a group. Its inverse must also belong in g, right? So g inverse is an element in g. Now what do we do? What do we have to show at the end? We have to show that x1 is equal to x2. Now observe, this element is in x. This element gx1 is in x, gx2 is also in x. So we can't simply take G inverse on both sides on the left. We can't simply do that, right? Because what you see over here is an element in X, not an element in G. So we have to be clever and remember to use the group action given over here. We simply can't take G inverse in this equation, right? So what do we do? We know that from the group action, the G acts on X, right? So we will simply take phi, this is given the group action phi prime of G inverse Gx1. We will consider this element in this group action, and this is equal to phi prime of G inverse Gx1 is equal to Gx2. So this Gx1 I will on this side replace by Gx2. Right? Now what? Because this is a group action, we will simply use its definition and the two properties. This is equal to G inverse Gx1 dot. This is equal to G inverse dot Gx2. The second property tells you, the second property of the group action, which is this, tells you when you have G1 times G2x, you can write it as G1, G2 times x. That is exactly what we are going to do over here. So we write it as G1 in G inverse G x1, G inverse G x2. This is the identity. Identity times x1 equals identity times x2. The first property tells you identity times any element gives you that element. This also reduces to this, right? So remember, even though it seems like you're simply taking G inverse on both sides in this element, right? We have to utilize the group action, right? You must remember this element is an element in X, not in G. So we somehow have to get to G in order to get that in G inverse and cancel the G that you see over here. The only way to do that would be to use that group action. That is exactly what we've done over here. Okay, right. Hmm. So I'll write so that PG is 1 to 1. Now we have to show that this is onto. So let's take any element from the set. Let X be an element in X. Then we have G inverse X to be an element in X. What is this G inverse X? Once again, referring to the group action, this is actually equal to phi of G inverse comma X. Sorry, phi prime of phi prime. Because in this case, we define the group action to be phi prime of G inverse X. Right? So this is equal to that one. We know that once you apply the group action to this element, what you get is an element in X, which is exactly G inverse X. Now, when X is in X, we know that G inverse X is in X. So that when you find the function value phi G of G inverse X, we get this to be G times G inverse X. This is equal to, once again, going back to this group actions given by GG inverse X, identity times X, you have the X. Right? So G inverse X through this function is mapped to X. Therefore, is onto. Right? So sigma sub G is 1 to 1 and onto. So we can conclude that is indeed a permutation of X. Right. Okay, now going back to the statement once again, we have proved the first part. Next, we have to show that the map which is from G to Sx defined by this is a homomorphism with this property. Okay. We have phi from G to Sx by now this is group of permutations of X. We have to show that this phi is a homomorphism, right? How do we prove that this is a homomorphism? Homomorphism. Let's take any two elements G1, G2 from G, right? G1, G2 from G. We want to show that phi of G1, G2 is equal to phi of G1 times phi of G2. Now, phi of G is given by this mapping sigma G, right? So, how are we going to show that the condition holds? The condition meaning we have to show that phi of G1 times G2 is in fact phi of G1, phi of G2. What we are going to do is we will show that this equation holds for every x in x because these are maps. This is a permutation sigma G, this is a permutation sigma G. So to show that this holds, what we are going to do is we will take any element from x, and once you apply that element and take phi of G1, G2 of x, and when you find phi of G1 of x, phi of G2 of x, what you get on this side is the same as the element that you get on the other side, right? That is exactly what we're going to do. So let me write for any x. We have phi of G1, G2 of x to equal sigma G1, G2 of x, right? And sigma here is defined to be Gx. Sigma G is defined to be Gx. So we have G1, G2 x, G1, G2 x. Now, using properties of group actions, we can write it as G1, G2x, G1, G2x. So we have G1, G2x is simply what? Sigma G2 of x, right? And G1 is simply sigma of G1 of this element, which is sigma G2 of x. Now we are simply using the definition of function composition, the way we write it. This we can simply write as what? Sigma of G1 composite sigma of G2 of x. We will simply write in the multiplicative notation times sigma of G2 of x. Now, sigma of G1 is simply, if you go to this definition, phi of G1, we have this to be phi of G1 times phi of G2 of x. And this is true for any x, right? So that because it holds for any x, we have phi of G1, G2 to equal phi of G1, phi of G2. Hence, phi is a homomorphism. It's a homomorphism, and we had to show that it's not just any homomorphism, it holds this property. We will simply apply the, hence phi is a homomorphism. I'll write with the property phi of G of x, by definition of phi of G, is simply sigma G of x. Sigma G of x is simply what? Gx. It's simply a matter of writing it out. There's nothing to really prove there. Okay. Do you have any questions from that? Okay.
Madam.
Okay. Before we get to examples, Let's take a look at this one, Sure. Let's take X to be, suppose X is a G set. What does it mean? G acts on G acts on X. So let's take the group action to be in the usual notation phi from G cross X to X with phi of G comma X denoted by Gx. Right? Now, consider a subset of G. Let's take N to be a subset of G such that N is the set of elements in G where Gx is equal to X for all X in X. So what sort of elements are we collecting now? First, we have this group action. G is a group. Now, we take elements from G which fixes all of X. What do I mean by fixes all of X? What do I mean by fixing an element? Through this group action, Gx will simply equal to X. Or we take, when you take the pair G and X, you have this element X taken from the set, right? And we know that this function value is a value in X. So what we are doing is, we are going to find values in G so that when you take this pair, this X that you take in the pair is mapped to itself. This pair is mapped to the X that is over here. In other words, Gx equals X. Once again, what sort of elements do we collect in this case? What sort of elements do we have in N? All elements in G that fixes every element in X. Now, this N is actually a normal subgroup of G. This we are going to prove. N is a normal subgroup of G. We have N to be a normal subgroup of G. So what we are going to do is we will first show that N is a subgroup of G. Then we will show that the normality condition also holds. To show that it's a subgroup of G, we will use the subgroup criterion. So we must have at least one element in the set N. In other words, the identity must be there. Is the identity there?
Yes, madam.
Yes. How do we know that the identity is in there?
T times E equal to E by definition of group identity.
Okay. So now there is a slight misunderstanding over there. What sort of elements that we take from here? Every element in G such that Gx is equal to X for all X in X. What is this Gx? That is exactly what you see over here, phi of G comma X. Right? Once you apply the group action to the pair Gx, you get the element Gx. And this is equal, we take all G, all elements in the group such that this pair is simply mapped to this element that you take from X, which fixes X. Okay, so the identity is in there, but how do we conclude that the identity is in there? If any G belongs in here, it has to satisfy this condition. So does the identity satisfy this condition?
Ex equal X, the definition of property of the action.
Group action, exactly, very good.
Yeah.
So we know that Gx is also an element in X, right? And when G is simply the identity, the first property of a group action tells you Ex must equal X for every X. So when you apply the identity, when you take the identity instead of G over here, identity comma X will be mapped to X, no matter which X that you take from the set, right? So the first condition of a group action tells you that it actually belongs in the set N, right? So let me first write. First, we will show that N is a subgroup of G. Observe for E in G, EX equals X for all X in X, so that E belongs in N. N is not empty. Okay. Now to use the subgroup criterion, what do? We take two other elements, G1, G2. Right? And we will show that G1, G2 inverse also belongs in N. Let G1, G2 belong in N. Then we have, by definition of the set N, we have G1 x2 equal X and G2 x2 equal X for all X in X. Right? Now these two elements are taken. We will show that G1, G2 inverse is in N. G1, G2 inverse is in N. How do we show that this element belongs in N? How do you show that this element belongs in N? It has to satisfy that condition of the set, the definition of the set. In other words, we must show that G1, G2 inverse dot X must equal to X for all X that you take from the set. This is what we have to show. Okay. Now, the first thing that we have to see is instead of G2, we have G2 inverse, right? G2 inverse. So now observe that G2 inverse dot X, I can write as G2 inverse dot X, I will replace by G2X. Why is that? Because G2 is taken from N for any X. For any X, X is equal to G2X. So this X that you see over here, I will simply replace by G2X. Right? Because G2X is equal to X. This is equal to, using the second property of group actions, I will consider these two together, G2 inverse G2 dot X. G2 inverse G2 is simply the identity. Identity times X is equal to X. This is true for all X that you take from the set. So now we have G2 inverse dot X to equal X for any X that you take from the given set. By definition of the set N, G2 inverse must also belong in that. Therefore, we must have G2 inverse to belong in N. Right? G2 inverse also to belong in N. Now, let's go back to this one. Let's calculate G1. Go back over here and let's start with the left-hand side. G1, G2 inverse dot X. This is equal to, using once again the second property of a group action, we see this is equal to G1 dot G2 inverse X. Now, G2 inverse X is equal to X for all X. So we have G1 dot x. This is for all x in x. And G1x, if you go back over here, G1 is taken from the set N. Therefore, G1x equals x for all x. So this ends up being simply x for all x in x. Therefore, by definition of N, G1, G2 inverse also belongs in N. By the subgroup criterion, we conclude that N is a subgroup of G. N is a subgroup of G. Okay, now we have to show that it's not just a subgroup, it's a normal subgroup. So we have to prove the normality condition, right? Let me write to prove that N is actually normal in G. We need to show by definition G inverse NG belongs in N for each G that you take from the group and N that you take from this capital N. Right? Okay. So we want to show that this element belongs in N. In other words, what we have to show? We have to show that this element also satisfies the definition of the group N. That is G inverse NG x equals x for all x in x, right? So let's start off with this side. We'll start off with the left-hand side. We have G inverse NG x. This is equal to, I can simply use associativity property in within parentheses over here because G inverse NG is an element in the subgroup N. So what I'm going to do is I will write it as G inverse N times G dot x. Now this is like having G1, G2 dot x. So we are going to use the second property of a group action here. We have G inverse N dot Gx, right? This is equal to, once again, Gx now is an element in x by definition, right? So if you see the term that's on your left, G inverse N, this is like having the product G1, G2. Once again, we are going to apply, once again, we are going to apply the property, the second property of a group action. So we end up with G inverse NGX, right? Dot NGX. Now this is equal to G inverse dot Gx. Why is that? Why do we have this to equal Gx? N times N dot Gx to equal Gx. Observe that this simple N is taken from this group. What sort of elements do we have here? Well, N is taken from here. This implies by definition, Nx is equal to x for any element that you take from the set. And I told you for any G dot x is an element in x. Once you apply the group action, you go back to the definition once again of a group action, here you take any pair of elements G comma X. Once you apply this, it will be denoted by Gx. So this element, right, once you apply this function, the function value is a value in X. So for any G, Gx belongs in X by definition of a group action, right? And this simple N is chosen from capital N. Therefore, for any X that you take from the set, Nx must equal X. And we know that. And we have that Gx to be an element in X. So, Ngx must equal the element Gx. Right? This is why we are able to replace Ngx simply by Gx. So going back to the calculation once again, this is equal to, we are at this point, G inverse dot Gx. Once again, applying the second property of a group action, this is equal to G inverse G dot X, that is the identity dot X, simply equal to X for all X in X. Hence, by definition of the group N, we see that G inverse Ng belongs in N. So, by definition of a normal subgroup, N is normal in G. N is a normal subgroup in G. Right. Oh, sorry. Do you all have any questions from this?
No, madam.
Okay. Now, the N that we just defined is a normal subgroup of G. So we can define the quotient group G over N. This is well defined because N is normal. This is well defined. What sort of elements do we have in here? All left cosets of N by elements in G. Right? Now, with this, we can actually take X to be a G over N set as well. And how do we define the binary, sorry, not the group action in that case? Let me write, we can regard where the group action, let me denote it by phi prime of a coset Gn on X is given by Gn dot X simply Gx. Gn dot X, we will simply map it to Gx. Take this representative and simply apply that group operation. In other words, we can see if we write it formally, this is from G over N cross X to X defined by phi of Gn comma X to equal Gx. Okay, now let's take a look at some examples. Examples of group actions. Okay, first one. Let's take G to be a group we can write G as a G set itself, right? We can regard it as G is itself a G set. So G is acting on itself. There is a group action you can define from G cross G to G. Something very similar, right? We've seen this sort of function before when we define the binary operation, that is. How do we define this? Take G1, G2, and we simply consider this to be the product, G1, G2. When I say product in this case, now observe, take a pair of elements, an element from G cross G. So you're taking two elements, G1, G2 from G, and you simply apply the group operation, the binary operation. G1 times G2. So when I say times, in this case, we are simply meaning the binary operation over G. This we simply call the left multiplication. Left multiplication. Right. So you can easily see that this is indeed a group action. If we write it out, phi of EG, where E is the identity, is simply equal to E times G. The identity, definition of the identity yields that this equals G for all G in G. And then for G1, G2, and G, all taken from this group. If we write G1, G2, comma G, this by definition is G1, G2 times G. And this is an element in G. So we use the associative property to write G1, G2, G. This is equal to what? Phi of G1, comma G2 times G is simply phi of G2, comma G. For all G1, G2, G in G. Right? So the conditions are, sorry, conditions are satisfied. This is, you can easily see that this is a group action. Now, if we have, say, subgroup H of G, then we can regard G as an H set, right? In this case, we can write is an H set. Then we can regard G as being an H set. So now we define the group action from H cross G to G by once again taking an element from H, element from G. Consider simply the left multiplication HG, where between these two we have the binary operation of the group G. Observe H is a subgroup of G, right? What you have over here is an element in G. Now observe that when H is a subgroup of G, we regard G as an H set, not the other way around. We don't have H to be a G set, right? Because for every element that you take any G and any H, GH does not necessarily belong in G. If you take both elements from H, because H is a subgroup, yes, definitely the product will be there. But when you take one element from G and one element from H, it doesn't necessarily mean the product will be in H. So when H is a subgroup, we take G to be an H set, not the other way around. Okay, right. So this is also easy to see. Once again, over here, H is a subgroup, identity is in there. All these are simply applied. The same thing. It's easy to see. This is also a group action. Now, for a subgroup H, I'm going to define a different group action. Let's take G to be a group, H to be a subgroup of G. Right? Then G is said to be an H set under conjugation as well. What do we mean by conjugation? We've seen this previously, right, at the very beginning of today's class. So we define phi from H cross G to G by taking phi of H comma G to equal H, G, H inverse for all G in G, for all H in H. Right, so first we had to show that this is a group action. To prove the first condition is met. Now observe that H, G, they're all H is taken from H because this is a subgroup of G. This simple H belongs in G as well. So we see that this element is indeed an element in G. Now, to show that the first condition is satisfied, if we consider phi identity times G. Now, H is a subgroup once again, therefore the identity is in there. This by definition is what? Identity G, identity inverse. Inverse of the identity is simply the identity. Identity times G is simply G. This is equal to G by definition of the identity. First condition is satisfied, right? Now to see the second condition is also satisfied, let's take any two elements H1, H2 from H and G, an element from G. Phi of H1, H2, comma G is by definition H1, H2 times G, H1, H2 inverse. This is equal to what? H1, H2, G. When you take this inverse inside, when you find the inverse of the product, what do we have? We have H2 inverse times H1 inverse. This is what you have. The inverse of H1, H2 is equal to H2 inverse times H1 inverse. Now we are going to use, now we are in the middle of proving the second condition. We are simply going to use the associativity property, right? So what I'm going to do is I will keep H1 here, H2G, H2 inverse I'll calculate first, then take H1 inverse. We have H1. What is it that you see over here? This is simply phi of H2 comma G. So phi of H2 comma G is an element in G. You have H1, which is coming from H, H1, some element in G, H1 inverse. So the definition of this group action tells you this is equal to what? Phi of H1, this element, which is phi of H2G. Right? This is true for all H1, H2 that you take from the subgroup and G that you take from the group. So the two conditions are satisfied. This function, this mapping that you see over here is indeed a group action. Okay. One more example. Okay, once again, let's take G to be a group. Oh, and the other one. Now, over here, we have taken H to be a subgroup of G, but G can be a